Hi, we are from Group 2. Me and my friends will explain about pulse modulation and also multiplexing. Firstly, introduction to pulse modulation. Pulse modulation is a type of modulation where signals are transmitted in the form of pulses. What makes it unique is that it allows us to send analog information by sampling continuous signals at regular intervals. Pulse modulation can be classified into two major types, which are analog pulse modulation and also digital pulse modulation. In analog pulse modulation, the amplitude of the sample is infinitely variable. This means that the sampled signal closely resemble the original analog signals without being restricted to fixed levels. Common techniques in analog pulse modulation are pulse amplitude modulation, pulse width modulation, and also pulse position modulation. On the other hand, digital pulse modulation converts the sampled amplitude to the nearest predetermined level. It essentially quantizes the signal, making it suitable for digital transmission. Example of digital modulation is pulse code modulation. Now I will explain the difference between all of the pulses. PAM adjusts the amplitude, simple but noise sensitive. PWM adjusts pulse width, ideal for device control. PPM adjusts pulse position, and grid for precise system. And lastly, PCM converts signals into binary for digital transmission. Now, let's talk about sampling theorem. Sampling theorem is a fundamental concept in signal processing. It tells us how to properly sample a continuous signal so that we can fully construct it without any loss of information. The theorem states that a continuous signal can be completely represented and reconstructed from its sample if it is sampled at a rate that is at least twice the highest frequency present in the signal. This minimum sampling rate is called Nyquist rate. If the sampling rate is lower than the Nyquist rate, something undesirable happens, which is aliasing. Aliasing is when different signals become similar from each other in the sampled data. And to prevent from aliasing is to apply a low pass filter before sampling. This to remove high frequency component that could cause aliasing. Next is quantization, an essential process in converting analog signals into digital signals. From the graph here, we can see the concept of quantization. The smooth continuous curve represents the original analog signals. This is the signals that we want to digitize. The staircase-like shape shows how the analog signal is quantized into discrete level. Each step corresponds to a quantization level, which is a finite value representing the signal's amplitude at a specific point in time. The binary numbers on the left represent the digital code assigned to each quantization level. These binary codes are used to digitally store and process the signal. The difference between the original analog signal and the quantized steps is called quantization error. This error results from rounding the continuous signals to the nearest quantization level. Higher quantization level can reduce quantization error but require more data for representation, while fewer quantization levels will increase the error but reduce the data requirements. This process is essential for converting analog signals such as sound or temperature into digital formats for computers, communication, or storage system.
Now, let's talk about bit depth. What is bit depth? Bit depth refers to the number of bits used to encode the information for each unit of data. It plays a crucial role in determining how much details and precision a digital system can capture and store. For instance, a sample with a 24-bit depth can capture more subtle details and variation, providing greater precision compared to sample with a 16-bit depth. When a signal is sampled, the audio information must be stored in bits. This is where the data come into play. Higher bit depth is required for more accurate recording, as it allows for finer gradation of the signal. Next, bit depth consideration. When a digital sample is taken, the ADC essentially asks what is the amplitude of the signal at this moment. The answer for this question determined by the bit depth. So, what does the bit depth do? First, bit depth defines the number of possible amplitude level or step. Based on the picture, we can see that the higher the bit depth, the more precise the representation of the signal. This allows the smoother transition between levels, reducing noise and distortion. Second, bit depth also set the system capacity to handle the loud signal. Bit depth determines the system dynamic range, the range between the softness and loudness of sound the system can accurately capture without distortion. For example, DVD audio uses a bit depth of 16, meaning there are 2 to the power 16 possible amplitude levels available for representing the sound. If we calculate 2 to the power 16, we can get 65,536 steps. Since the range is split between positive and negative value, it means there are 32,768 positive value and negative values.
So next, we move to basic concept of multiplexing. Multiplexing is a technique for merging numerous signals onto the same transmission media to make the best use of available capacity. It divides the transmission line into channels for data transfer, allowing numerous transmitters to share it.
There are three types of multiplexing. The first one is frequency division multiplexing, FDM, time division multiplexing, TDM, and lastly, space division multiplexing, SDM. So the first one is about frequency division multiplexing, FDM. FDM is a method that divides a single physical medium's bandwidth into many separate, smaller frequency channels. FDM is mostly utilized when the bandwidth of the link exceeds the sum of the bandwidth of the signal that need to be sent. So each signal is modulated onto a unique carrier frequency, ensuring simultaneous transmission without interference between signals. There is guide band separate the signals to prevent overlap and interference, and a demultiplexer at the receiver and extract individual signals from the combined frequency spectrum. Next, we move to time division multiplexing. TDM is a digital method that divides data streams according to time. Each signal is transmitted at its assigned time slot once a channel is divided into time slots via TDM. In digital telephony, TDM is frequently used to send many conversations across a single channel. At the transmitter end, data from the different sources are sampled and assigned to time slots in a cyclic pattern. At the receiver's end, a demultiplexer reconstructs the original signals based on their time slots. There are two types of TDM. The first one is TDM PAM, which the signal is sent in form of a PAM sample that is multiplexed with other PM samples that contain other information. The other one is TDM PCM. The bits multiplexed and delivered for different information, and the sample must be converted into digit form. Last but not least is about space division multiplexing. SDM is a communication technique that increases the amount of data transmitted by separating single paths into multiple conductors. Each signal is sent in a separate, isolated area to prevent interference. Signals are transmitted in parallel, utilizing multiple spatially distinct channels, and at the receiver end, the signals are separated based on their spatial path. And for SDM, when we're using the smart antenna, digital signals processing is required, as you can see in the photo.
Next, I will be discussing the recent advancement in digital communication, focusing specifically on 5G technology. First, what is 5G? 5G stands for the fifth generation of cellular technology that is designed to boost speed, minimize latency, and improve the flexibility of wireless service. Additionally, 5G supports a converged network which combines licensed and unlicensed wireless technologies that helps to increase the availability of bandwidth for users. Now, let's talk about the relationship between phase modulation, multiplexing, and 5G technology. Modulation and multiplexing are key techniques used to maximize performance efficiency. One example is continuous phase modulation that functions to smooth phase transition, minimize signal distortion, and improve transmission quality. Another important technique is orthogonal frequency division multiplexing. This divides the available bandwidth into orthogonal subcarriers, allowing simultaneous data transmission without interference. Next, let's explore how 5G can impact the real world. Firstly, it enhances mobile connectivity by offering faster speeds, seamless streaming, and gaming, even in crowded areas or rural settings. Secondly, it impacts in revolutionizing healthcare by supports wearable health device that monitor patient vitals and send real-time data to healthcare providers. Thirdly, 5G helps in advancing the industrial automation like cabinets, robots, machines, and sensors, enable real-time monitoring and predictive maintenance in industries. Lastly, it helps in agricultural transformation by enabling drones and IoT sensors to monitor crops, soil health, and weather, optimizing yield and reducing risk.
Let's address some common misconceptions about post-modulation and multiplexing. First, there's a belief that post-modulated signal pose a health risk due to radiation. This is incorrect. This signal uses non-ionizing radiation, which is safe and doesn't harm DNA or cell. Regulatory bodies like the WHO ensure strict safety standards for electromagnetic exposure. Second, people often think multiplexing increase interference or lead to data loss. However, advanced technologies like error correction code and adaptive algorithms are designed to prevent this, ensuring data remains intact and with minimal interference. Lastly, there are privacy concerns. Multiplexing combines signal encryption and global data protection law such as GDPR to safeguard user information and ensure privacy is maintained. In summary, pulse modulation and multiplexing are the backbone of modern communication system, enabling faster, secure, and reliable data transmission. Despite the misconception, these technologies are safe, efficient, and transformative with significant benefit for society. They connect people, support critical sectors, and drive innovation. By addressing concerns with accurate information, we can embrace their potential to build a more connected and inclusive future.